All right, the next thing we're going to talk about is the convergence of a Taylor polynomial or a power series. A power series is just like a Taylor polynomial. It just may not be built that way, but it's not important to us how it was built. It's just a power series. So you're going to have something with all those powers. The ones we've built are the Taylor and Maclaurin. Okay, first thing we want to consider is that we should not build Taylor polynomials where it doesn't make sense. So here, if I plug in x equals 2, that's perfectly fine. And every derivative I take, it's still going to be able to be plugged into. We're never going to have 0 on the bottom. So it's a fine one. If I try to take this create a polynomial for this centered at 1, that doesn't make sense because the natural log of 0 is an asymptote. You're not going to build a polynomial around an asymptote. This one should say no. Don't know why I wrote yes on accident. Sine over cotangent is cosine over sine. The sine is 0 is 0, so that doesn't make sense. It'd be undefined right away. Building a Taylor polynomial at -1. Well, the first derivative I take is going to give you 0 on the bottom. Taylor polynomial centered at 0. Our function's imaginary. Again, we're not going to have imaginary numbers. And this one's just geometric, and geometric you can build wherever you want. This is a fun fact to show you how well these polynomials and stuff work. If we use 39 digits of pi to calculate their circumference of the observable universe, it'll calculate it to within a width of a hydrogen atom. That's pretty incredible for how big of a thing that you're approximating, and the air is smaller than a hydrogen atom. And that's why these Taylor polynomials are so strong and so useful. We can get incredible air without much work. I mean, it's work, but I mean, it's better than other things. All right, so the first thing we're going to do is build a Taylor polynomial. I'm trying to find my eraser. So here, f of x, we're going to build the Taylor polynomial of natural log of x, and we're going to build that at x equals 1. Why wouldn't we do it at 0? Well, we just talked about it. It's not a great place. Natural log of 0 is undefined. So we go through and take our derivatives, and this time we're going to evaluate everything at x equals 1. Natural log of 1 is 0, so that's your constant. The next one, when you plug in 1, you get 1. Remember, this is your x minus 1 term because we're centered at 1. This one right here is going to be your x minus 1 squared. So this Taylor polynomial is another one you probably want to memorize. Notice that the natural log 1 does not have factorials under it, just like the geometric didn't. They naturally got absorbed with our derivatives. So right here, it'd be 3 over 4 factorial. So that's 3 over 4 times 3 times 2 times 1. I extrapolated wrong. This should be 6. We just kind of saw what the pattern was. So here, we'd have a 6 on top, which would cancel these guys and leave us with the 4. And then each time this is going to be 1 less factorial, so it'll cancel nicely. So the next one's 5 factorial, so what's going to be on the top is really 4 factorial, and they'll cancel to be 1/5. All right, so then this is the general thing with the natural log of x is approximately equal to when it's centered at 1. If we want to know what the value is at x equals 2, and whether it converges or not, all I'm going to do is take 2 and plug it in there. So 2 minus 1 is 1. So I don't really need this 1 at the end because it doesn't mean anything. So what I'm left with is this. So really n plus 1 here. But look at that. What is -1 to the n over n? Well, that's an alternating p-series. So alternating p-series with p equals 1 converges. Now it is a conditional convergence. Not important. It just converges. So 2 questions we want to know is when the power series converges or diverges. What test do we use for it? If it's geometric, we're just going to use r is less than 1. If we want to do anything else, we have to use the ratio test. So what we're doing right now is we're figuring out how far from where we evaluated where we centered the polynomial, where it was exact, how far can we travel to the right or left and still get a valid answer? So one choice is that it can only converge where it's centered. That's a silly problem because we know where it was centered. We know all those values. Why would we have a polynomial for that? The next one is the absolute best. Radius is infinity, which means I can travel as far as I want on the number line from C. So what we want to think is factorial on the bottom. If there's a factorial on the bottom, it's going to converge everywhere. So think about your cosine x. That's going to have an infinite radius convergence. Sine x, that's going to have an infinite radius convergence. E to the x is going to have an infinite radius convergence. The next one is the one that's the most common, is that you can only travel a certain distance r in each direction. You want to get x minus c less than r. That's our goal. And that says that if it was centered at 0 and maybe the radius was 2, that means I can go all the way to 2 and negative 2. So looking at this first one, it's centered at 2. We do the ratio test. Remember, the ratio test is limit as n goes to infinity of an plus 1 over an. So that's what we wrote right here. And whenever we did this, the first thing we did is cancel anything we can. So here's an n. Here's n plus 1 factorial. Every single time we're going to check if the degrees are equal. The degrees will be equal if there was no factorial. So you see right here the degrees are equal. So it's the ratio of the leading coefficient, so it's just x minus 2. Now this is the part that everybody gets all weirded out on. This is the ratio test. What do we need for the ratio test to converge? The ratio test converges only when it's less than 1. Now look at, our goal was to get x minus c less than r, so r is 1. So that means if I'm centered at 2, I can go one direction, go one in the right direction and one in the left direction. Now, that means I can get anything in between there. Now I need to worry about those endpoints. Are the endpoints okay to use or not? So all we do is we take these two endpoints and we're going to plug them in for x. So we take x equals 1 and we plug it in here. So that's going to leave us with negative 1 to the n over n. Converges absolutely. Converges conditionally, sorry, because it's p equals 1. Now if I take the other endpoint, which is 3, and I plug it in here, you can see that I only get 1 on the top. This is harmonic, or p equals 1, it diverges. So on the left side, this one converges, which means you're going to include it. AP will also write it like this. And then right here, this one diverged, so at 3 you're going to have the open parentheses, or less than. Okay, so it's a lot of things we've already done before. It is a lot of steps. If you get this on an FRQ, it's 5 points. You get your first point from writing the ratio, the next point from finding the limit, the next one for stating what the radius is, 1 point that you check the endpoints, and 1 point that you got it correct. I want to show you the 2 other cases with infinite radius of convergence and 0 radius of convergence, just so you can see what it looks like, and then we'll do more practice of the first one. Okay, so looking at this one, the first thing I notice is factorial on top. If the factorial is on top, it's growing so fast. It's not going to converge anywhere except for where it's centered. Let's go through the test. So the ratio test, here's an plus 1 over an. So now looking at that, we cancel what we can. We have n plus 1 factorial over n factorial, so that leaves us with n plus 1. We cancel our x's, so we're really left with this. As we're sending into infinity, this is going to infinity. Remember, our goal for the ratio test was to make this less than 1. That's never true, which means the radius is 0. You're only going to converge where you're centered. The other case, if there's a factorial on bottom, we expect infinite radius convergence. Again, the ratio test. Be careful here, because when we're replacing n with n plus 1, it's really 2n plus 1 plus 1. So that works out to actually be 2n plus 3, and same thing right there. So be really careful when plugging those in. Again, we cancel everything. So we cancel our alternating. We're inside absolute values. Alternating doesn't mean anything. This one and this one cancel, but remember this was 2n plus 3, so there's actually x squared on top. Our factorials leave us with some stuff on the bottom. So the degrees are not equal. n is going to infinity, which means this is less than 0. This is going to be equal to 0, and we want it to be less than 1. It's always less than 1. So the radius of convergence is infinity, and it converges everywhere. If you get one of those on the AP test without endpoints, you get 1 for writing the ratio, 1 for writing the limit, and 1 for writing the radius. So 1 for the ratio, 1 for the limit, 1 for the radius or interval. Okay, so more practice on the other ones. Okay, so looking at this, we have this right here. We can see it's centered at 0. So we go through our ratio test, writing that out. We get 3 on the top over here. Remember, it's an absolute value. We also get an x over there. And there was no factorials, which means the degrees are equal. You can see that right here, the degrees are equal. So it's just the ratio of the leading coefficients. So there's 3 times the absolute value of x. And our goal was to get x minus c. Right now I have 3x minus 0 is less than 1. I don't want this 3 here, so we're going to divide by it. And that gives us our radius. We travel 1/3 from where it's centered. It was centered at 0. We knew that because it was x minus c right here. You do not see the c. So these are the 2 endpoints we're going to check. So I plug in -3. Remember, you plug that in for x. If you multiply those, -3 times -1/3 to the n, you're just going to get 1 to the n, which is just 1. This right here is a p series. P equals 1/2. It diverges. We don't include it. On the other side, when I plug in 1/3, we multiply these, we get the -1 to the n, so it alternates. And alternating p equals 1/2 converges. Next one, centered at -2. So we do our ratio test. Notice that there's no factorials, which means I think I'm going to get a finite radius of convergence. Right here, I have x plus 2 left on top, 2 on the bottom. We need to force this to be less than 1 because that's what it means to be convergent for a ratio test. So we get the radius is equal to 2. We're centered at -2, which means I'm going to go to this direction and then to that direction. And we plug in our endpoints. So the first endpoint we plug in is -4. We plug it in there. Those -2 and 2 to the ends cancel and leave us with -1 at the end. This is p equals 2. Converges. Now this is p equals 2. It didn't need to alternate to converge. That's just a bonus, which means the other side is also going to converge. And they're both closed. Now one thing you'll start to notice is that every single time you do this, whenever you see this like exponential piece right here, right here, you expect that to be a radius. If it was on the bottom, it's going to multiply to the top. Over here, the 3 was over here. Notice my radius is 1/3. It was on the top, so now it's on the bottom. The only other thing that's tricky with this is geometric. Geometric is so wonderful because it saves us so much time. You do not have to do the ratio test. For geometric, we only need r to be less than 1. Now remember, if it's geometric, it looks like a r to the n. So r is x minus 1/4. So we need x minus 1/4 to be less than 1, which again looks like what we wanted. X minus c is less than 1. So you multiply by 4, and that's your radius. So much nicer into doing the ratio test. Now, the other great thing about that, geometric, the endpoints are always open. Let's think about that. Geometric says less than 1, it converges. Equal to 1, diverges. So we know on the endpoints it diverges, so both of them are always open for geometric. Now, why isn't that true for the other ones? Well, the ratio test converges if it's less than 1, but the ratio test is inconclusive at 1, which is where the endpoints are, and that's why you need to test them.